To understand calculus, you have to understand the problem that mathematicians in the 17th century was trying to solve. They were trying to find the gradient of a curve, or a tangent to the curve. I'm going to assume you already know how to find the gradient of a straight line. If you don't know how to find the gradient of a straight line, I highly suggest you watch the gradient video and then come back. Now, we all know that the gradient of a straight line, to find it, is rise over run. But if you have a curve, I'm going to show you a curve. There you go. If you have a curve, the tangent is where the line only touches one point on the curve. Notice also that the gradient of the tangent is ever changing on this curve. It goes from very steep negative gradient and then to less steep, and then it's now positive gradient, and it gets steeper and steeper and steeper in the positive direction. So the gradient is actually a function. It's another equation, right? Because depending on where the point is, the gradient of the tangent will be different. Just keep that in mind. If you only have one point, how are you going to find the gradient? Because for a gradient, you need 2 points. You need x1, y1, and you need x2, y2. What they ended up doing was they took 2 points on the curve. So let's say I want to find the gradient of this tangent at x is a half. So they thought, let's grab another point on the curve. Let's say they've brought this point in. And then they can find the gradient of this green line. Now it's close, but it's not quite right, is it? So they thought, okay, what if we get the point closer and closer and closer and closer to x is 0.5. So you can see now x is 0.6 and then 0.59, 0.58, 0.57. What if we bring it so close, so infinitely close, that we will eventually be close enough to find the gradient of the tangent? Now this is the whole basis of calculus, just going infinitely smaller, or going towards a limit. Let's figure out what we can do with the knowledge we just learned. Let's try and figure out the gradient of the tangent of this point, which will be something like that. But again, we can't do it with only one point, so we've got 2 points here. To get the gradient of these 2 points, we need the rise and the run. So we've got rise over run. That's normally what the gradient, how to find your gradient. The rise is just the change of y values, and the run is usually the change of x. It is the same in calculus. In calculus, we note it as delta y. So delta is this triangle here, dy over dx. It's all the same. It's just a change of y over the change of x. Rise over run. Okay, let's try and figure out what the rise over run is for this case. Now, they named the run h. They used h. I don't know why, but they picked h, and that's the run. So that's the distance of the difference between the x's. This point is going to be x, and then the y value would be f of x. This point is going to be x plus h is the x value, right? X plus the amount of h, that's the x value. And then the y value is going to be the function of x plus h. All good? I hope that makes sense. Now, what is the rise and what is the run? So the rise is y2 minus y1, right? y2 minus y1. The run is x2 minus x1. x2 minus x1. So that is going to be x plus h minus f of x over h. because the run is just h. We already know this, so that's good that it turned out correct. Now, if we want these points to get closer and closer and closer and closer to x, we want h to get to 0 or as close to 0 as possible. Therefore, we want to find the limit of when h goes to 0. The limit when h tends towards 0. Now note that h cannot be 0 because you can't divide by 0, but it can get as close to 0 as we want it to be. Right? Now this is derivative by first principle. I know it looks really scary. The first time I saw this, I thought, wow, what a huge formula. How can I ever remember this? But if you just come back to here, it is just rise over run. Just get 2 points on a graph. All you have to remember really that the run is h. If you can just remember the run is represented by h, then you can figure out the points, and it is just rise over run. Let's apply this to an example, and I'll finish it off with a shortcut for you. Now, let's call this parabola y equals x squared. Alright, and we want to find the tangent function. So, the tangent of any point on this curve. And we'll do it by first principle. Firstly, let's find the 2 points. So the first point will be x, and the y value would be x squared, because when x is x, y is x squared. Then the second point, the x value is x plus h. Remember, it's x plus however far away this is. And then the y value is when x is x plus h, so y is going to be x plus h all squared. Deriving this function, we have when limit is when h going towards 0. F of x plus h is this one here, x plus h all squared. Minus fx is the x squared all over h. That's going to give us limit of h going towards 0. Expanding this bracket will be x squared plus 2hx plus h squared minus x squared all over h. The x and the negative x, the x squared and negative x squared cancels. And then we have limit h towards 0. I can factorize the h out, and that will give me h outside of 2x plus h over h. The h cancels as a common factor. Then that becomes the limit when h goes towards 0 of 2x plus h, which is 2x plus 0, which is 2x. Therefore, the derivative of x squared is 2x. That means that we can substitute a value of x, and we can find the gradient of the tangent where x is. Let me show you. Let's say when x is 1, we should have a gradient of 2, because 2 times 1 is 2. Let's have a look. So when x is 1, we have a gradient of positive 2. Let's see, what else do we know? When x is 0, we should have a gradient of 0. Let's see. When x is 0, 2 times 0 is 0. The gradient is 0 when x is 0, which is true here. What about when x is negative 1? We have a negative slope, negative gradient. So when x is negative 1, we should have a gradient of negative 2, which, yes, it does look like a gradient of negative 2. All right, and this goes on at any x value. You can find the tangent, the gradient of the tangent using this function here, dy dx equals 2x. Now the shortcut. You don't have to do it by first principle every time, because when the mathematicians did this enough times, they realized that you can do this with a shortcut. So the derivative of y equals x squared is, you can bring down the power, so 2 comes down, and then minus the power by 1. So it's now just becomes 1, and then you have 2x. And you can do this with anything. For example, if you have y is equal to, say, 4x cubed, you have 3 comes down and you multiply it with the 4, so that's 12. X minus the power by 1, it'll be squared. So the derivative is 12x squared. And then if you have y is equal to, say, 3x, the derivative would be, bring down the power. Currently there's a power of 1, so it'll still stay as 3. And then minus the power by 1, so it becomes 0. X to the power of 0 is 1, so 3 times 1 is 3. And that is the basics of differential calculus. This is only half of calculus. The other half is integration, which is to find the area underneath a graph. But I'll do that in the next video. Till then, study smart, not hard.